Hi, welcome back to our lecture on neural networks. And this video will be about choosing the right optimizers for your neural nets. Now, we've already seen stochastic gradient descent, and it's a good starting algorithm, but we've seen that in many cases it doesn't converge as well as we'd like to, or it doesn't converge at all. And this has to do often with the fact that it uses a constant learning rate, eta. So it kind of assumes that no matter where you are in the training, where you are in the beginning or near the end, that you can use the same learning rate. And this doesn't always work out so well. So first, let's look at the surface. Typically, when you start at a random point, you're likely to start somewhere at a point where there is a high gradient. And then, yes, it makes sense to take big steps. But as you go towards some optimum, yeah, you see what this happens. So if your learning rate will be constant, you will start zigzagging a bit, and that's something you typically don't want. Now in this case, I'm over emphasizing this a bit, but this can happen if you keep a constant learning rate. So an idea to fix this is to add a decay. Right? So you start with an initial learning rate. Any new iteration, you multiply your current learning rate by some factor e to the minus ks. And what this will do is basically exponentially decrease your learning rate. So if this is your learning rate eta, and this is the step, so this is the iteration of stochastic gradient descent, then it would decrease exponentially. Now, how fast? That's controlled by the decay rate k. So you can choose to do it gradually or very fast or very gradually, depending on this hyperparameter k. So you again need to choose that. There are some good default values for that, but yeah, it's not a thing you need to tune. Next exponential is also inverse time, where we take our original learning rate, and every time we divide it by 1 plus ks. So also here, every time step, this gets smaller and smaller, more or less exponentially. We can look at what this does in practice. So here we have a surface. So we want to end up in this lowest point here with a star. We start out in this point here. You could also repeat this for any other point in this space. So yeah, let's start at the beginning. So we take one step, and we can compare normal SGD to SGD with weight decay. Now, the version with weight decay typically has a larger starting value for eta, so that's why it takes a bigger jump here. Now, then after this iteration, we compute the gradient at that point, and then we'll make a step in the direction of that gradient. Now, since vanilla SGD has a small learning rate, it will take a small step here, while SGD decay, well, it has a smaller learning rate than in the first step, but the learning rate that's we use here is still a bit large, right? And so you can see it takes bigger steps here. So every arrow here is one step of stochastic gradient descent. And we see that both algorithms do work towards the optimum, but we see that the decay one has a better, well, goes there a little bit faster than the other one. In fact, normal SGD starts really slowing down here, while with decay you get a little bit further closer to the true optimum. Right. Now, of course, this can completely change if you would run vanilla SGD with a tuned learning rate. Right? In this case, I just use the defaults. You can very much find the fastest solution if you tune the learning rate. Right? And so if you use SGD, that's definitely something you should do. You should definitely tune your learning rate to the problem so that you converge faster to a good solution. Let's compare to SGD decay actually. Right. So while SGD decay is now decreasing the learning rate, the cyclic version is increasing the learning rate. And so in the region when SGD decay starts slowing down, the cyclic one is actually speeding up. and hopefully we'll then also get to the optimum faster. It's a tight race. You can see that the error still gets smaller, and that's because, of course, the gradient gets smaller as well. And you see now the decay version is catching up. The cyclic version is catching up. It's surpassing now the decayed version. Yeah, here you can see diverging, right? So it got there fine, but then the limit became too large, and then it really diverges, right? So we really want to stop the training before that happens. And like I said, you would detect this by looking at the learning rate, the learning curve, sorry. And so say that this is the number of epochs or the number of batches. Look at, we'll see how learning curves work in a minute. But this is the validation loss, and this is the number of epochs for training. You will typically see that as you use the cyclic learning rate in the beginning, you will see the loss go down. This is what you see here, right? Here it has high loss, and here it starts finding a local optimum. Well, it will get pretty low, and then at some point it will start overshooting again. This is what you see here, right? So the idea is that we observe this learning rate and we stop before that happens. So you can do this manually, but you can also just check whether the validation loss doesn't go down anymore for a number of steps, and then just stop there. Right? So yeah, it's a slightly less used technique, but it's often useful in many applications. And there's the final one, which is also sometimes used, which is the warm restarts. So the idea there is that you don't have like one cycle, but you have multiple cycles. So if this is the number of steps, and this is the learning rate, what you do is typically you decrease the learning rate at some point, and then you increase it again, and then you decrease it again, and then you increase it again. There's different ways of doing this exactly, but the principal idea behind this is that if there's a scenario where learning rate is too small, you kind of escape it, and you have larger learning rates again, which may help you like escape the local minima or speed up the search for the optimum. And then, well, if this decision was wrong, it's not so bad because later on you will get back to the learning rate, which is small again. That's the idea behind warm restarts. Now, a very useful technique is momentum. So the idea here is that imagine that you have a ball, and this ball rolls down our gradient surface. Right, so you start at some point here, and then you end up here. Now this ball is rolling down the surface, and in the previous time step, it made a jump from here to here. Now, if you know momentum gives as well speed to a moving body in a certain direction, right? So what it will do in this case is that instead of computing the gradient here and then moving in this direction, it would also keep moving in the same direction it was already going in, times some parameter gamma. It's called momentum factor. So this green arrow is basically 0.9 times this gray arrow. So this was a previous update. So this is basically Vs minus 1. And then the next step, the green, that's the actual step that you make, is gamma times our previous vector. Right? This gives us the green one. Then we compute the gradient in our new location, and this tells us to go in this direction. That's the red term. And the actual movement that you make is the sum of these, right? So take the green one times the direction of. So this is minus the green, of course, and sum these two up, and you end up in this point here. So that's the blue vector here. That's the idea behind momentum. Momentum is typically very useful, especially because it makes sure that your trajectory is not influenced by some local aberrations of the, the surface of the loss function here. And if you would have like normal SGD, it can happen that you start zigzagging, or say that you end up somewhere here, you go down again, and then down again, and then maybe up again, and down again, and you sort of avoid that by having this momentum. So if you would come in, say, from here, because that's the prevailing direction of the gradient, then instead of doing the zigzagging, you would have a reduced zigzagging towards the optimum. Right. So the idea is that the momentum, hopefully, momentum has basically information about what the gradient has been doing in the past, right? It kind of encodes that information. What's the general direction of the downward slope? And then adds that to any local observations of the surface. And hopefully that will give you a faster convergence to the optimum. Now there's one variation which is very popular, which is called the Nesterov momentum. So the idea here is that you don't compute the gradient at your current location, but you compute it, well, you know that the ball is going in this direction, right? So you might as well be interested in what the surface looks like in that direction. And so that's what Nesterov momentum does. So it looks, so this is again our previous vector v. We have this exact same momentum term, which brings us here. And then you compute the gradient in this location, right? And this tells us, oh, you have to go back. Right? And then effectively our final actual step will be this one. Right? So overall, you can see that, well, in this scenario, you definitely go faster towards the optimum than this case where you would likely start zigzagging also a bit. Right? So Nesterov momentum is a pretty good technique to help solve that. It helps solve the overshooting problem that you often see with momentum, especially if you end up having large speed. Another way that you can avoid having too large momentum is to not use a fixed momentum factor, but to change the factor over time. So you can start with a very low momentum, like 0.5. So if you are at some point initially, you're likely to have a strong gradient. If you have a strong gradient, you don't need large momentum, right? So you don't want to go too fast, right? Strong gradient plus large momentum means you're going really, really fast, and you want to avoid that because that may start overshooting. So well, in the beginning, you assume that you are at a high gradient position and you then make smaller steps. And then later, when you end up in the valley, then you will start having more momentum just to keep the ball rolling so it doesn't stop. Right? So you can, depending on the surface, you can increase this to 0.9 or even to 0.99. Okay. Let's see how this behaves in practice. So here again, we have a normal SGD, and now we can add momentum. So you will see the momentum, well, while the initial steps are smaller, you can see that it's not affected, like the normal gradient descent would end up here and immediately change direction. Momentum doesn't do that, it's much more gradual. So it will change direction, but more slowly than gradient descent. And in this case, it actually starts overshooting a bit until it bumps into this region, turns over, goes back, and so on. But even though it does overshoot, you can see that it does get there faster eventually than normal SGD. Right? So while normal SGD is now going at a snail's pace towards the optimum, the momentum still has a lot of speed. It will start probably overshooting still, but it will get faster to an optimum. If you compare this to Nesterov momentum, it's similar, but it will be much more dampened, much more docile than the normal momentum. Takes a while. Oh, it's still computing here. This is Nesterov, and you will see that, well, it overshoots less than no momentum, right? So it bends quicker. So it reacts faster to any local changes that it finds. It also bumps into this wall here and then corrects and then speeds up again here. If you would look at the time it takes to get there, then you will see that, well, in this case, Nesterov does get there a bit faster and doesn't oscillate as much, although the difference is really, really small here. Right. Now, we're still using the same learning rate for every weight. And, well, it's been observed quite early already that this is probably not a good idea. Why? Because different weights are in different locations in the neural network, right? So some weights are in the beginning of the network, others are much further away. So say you have a network with many, many layers. So you have all these layers. If you have a weight here, first of all, it's going to have much smaller gradients than the weight here. Right? So, and this is probably important to set the learning rate. Right? If you are dealing with large gradients all the time, you can get away with a smaller learning rate. If you are dealing with very small learning rate, very small gradients, you probably want a bigger learning rate. Another factor could be that you have a neuron which has many, many inputs versus one that has few inputs. So again, in this case, it will get updates from many different other nodes, and this will definitely give it a large activation, right? So you may want to deal differently with this one than with a node which only has a few inputs. So the idea behind adaptive gradient is to do gradient descent as usual. So this is exactly the same formula as we used for normal SGD, but we add a correction to the learning rate. Depending on what the gradients look like for this weight. And we can do that by looking at the previous gradients that observed, right? So we over time, we look at the gradients, right, with respect to that weight. We're interested in the relative magnitude, so we square those, so there are positive. And then we take the sum of all of these, right? So this factor G tells us whether that connection, that weight, typically deals with large gradient or small gradients, right? So if it deals with large gradients, then we reduce the learning rate. If it deals, so that's why we do n over g. If it deals with very small learning rates, then this will be small. We want this learning rate to increase. Right? So that's the whole idea behind this. Now, ideally, you may want to have a simple thing like n over g. Oh yes, and people have been looking at that, but it turns out that the square root actually works better than not using a square root. So yeah, we use the square root here. And there's a very small factor e, y, just to avoid division by 0, because it's possible that the GIS becomes 0. By the way, I'm using index notation here, just to let you know that these are calculated per individual weight. Right? If I would show the vectorized representation, you may forget that this is actually computed per weight independently. Right? So it has a bit more indices here, but this is to remind you that we do this per individual weight. Okay, so this algorithm is called autograd. It's very, well, it's used to be very popular. We have better versions now, but that's the idea behind it. Typically, we have a typically small learning rate n. Why? Because, well, actually, the learning rate doesn't really matter because you will adapt anyway to the local situation of the neurons. But you do not want to make this too large, otherwise it may not recover fast enough. So take one small value for the learning rate, the initial learning rate. It can be 0.001 or 0.01. And then afterwards, let the algorithm itself learn basically how to scale this learning rate for each weight independently. Now, autograd still has a few issues, and it has to do with the way that we define G here. First of all, it's a sum of squares. So this will get bigger and bigger over time, and this means that this term will get smaller and smaller over time. So it can slow down learning. A second problem is that, say that in the beginning of the training you had very large gradients, but then afterwards the gradients get very small. Then this term GS will still be very large, even though the recently seen gradients are very small. Right? So an obvious solution to that is rmsprop, which replaces this squared sum with a moving average of the squared gradients. Right? So if you look over the gradients over time, it would basically pay a lot of attention to the recent ones, and the older ones will be weighted less and less. It's kind of exponential moving average over all the observed gradients. So formulaically, it means that our correction mi is our previous correction mi times a factor of y plus 1 minus, gamma, plus 1 minus gamma times the currently observed gradient. Right? So gamma basically defines how important the past is. Typically, we set gamma to something like 0.9, which means that this correction factor m is 90% defined by what the general size of gradients is, plus 10% what the current grade is. Right? And this avoids that these gradients dwindle down to zero as GI grows. And the rest is the same. Right? We basically just replace GI with MI here. We replace the sum of the squared gradients with the moving average, exponential moving average of the squared gradients. And by the way, if you find the name confusing, so rmsprop stands for root mean square prop. Prop comes from another algorithm called rprop, which they change here. And the root mean square error points to the fact that you take an average, moving average, so a mean of the squared errors, and at the end you take the root. Right? That's root mean squared prop. Okay, let's see how they behave in practice. So here we have again our surface, we have SGD, and now we compare that to autograd. So see, autograd definitely has a smoother movement through this space. Why? Because in SGD, the gradient update can be influenced a lot by a few weights which have a large gradient. Right? So that it can change quite fast. While in autograd, there's a more balanced contribution for all the weights. So we have like a smoother curve through this space. We can also compare this to rmsprop, which will look almost the same initially. Right? The only difference is the the contribution of each weight is more or less the same initially, but the size of the unit will change with rmsprop. And we already see that while eta is already stuck here, rmsprop has gone a little bit further there. So if you move this, so yeah, you can see that rmsprop is speeding up, and if we take a few more iterations, we can see that rmsprop gets down to the optimal solution actually very fast, faster than anything we've seen so far. And there's no zigzagging whatsoever happening. You can see it goes to the optimum much faster than normal eta. Another fun thing you can do, you can also add momentum to rmsprop. We'll see how in a minute. And this will typically give you a much more active, faster. It will start overshooting a bit, but it overshoots definitely less than normal momentum. So this is RMS with momentum, so it does overshoot, but then corrects, and actually is a lot faster, I think, than the other ones. So if we take it at 40 iterations, you can see it overshoot and then start zigzagging a bit in this space, while the normal rmsprop goes very smoothly to the optimum. And you could also compare this to normal momentum. And you see that while rmsprop with momentum overshoots as well a bit, it's much more docile and much more targeted than the normal momentum or even the Mestrov momentum. Although in this case they're pretty comparable. Right. So how do we add momentum to rmsprop? This was actually first introduced with an algorithm called Atom. So the idea behind Atom was exactly this, to have rmsprop with momentum. And what it does, it basically adds the moving average of the gradients as well. So let's back up a bit to momentum. Right? So what momentum does, it takes the gradient update and adds this momentum step to it. Right? And that's our new update V. What we do in Atom is exactly the same. So we replace the gradient by this new term g, which has this momentum parameter times the prior vector g plus 1 minus that vector gamma 2 times the actual gradient. Right? So this basically adds this term weighted by a vector gamma 2 in this case, and adds that here, and then basically adds it to the same formula we had for rmsprop. Right? So rmsprop was this. So what we do in Atom is we replace this term with this term, which adds this momentum vector to it. That's basically what it does. Now, if you would use rmsprop with momentum, you would do exactly that. The actual Atom algorithm has a few more changes. For instance, it adds a bias correction because they observed that in the first few steps of gradient descent, you will get very, very, very small gradients. So it learns very slowly in the initial few steps. And this bias correction kind of reduces this effect of this correction factor so that it's, especially initially, speeds up training a bit. In practice, the effect of this bias correction is really small, so people often don't worry about it. If you're going to do like 50 iterations anyway, then or 100, then having a few slow steps in the beginning doesn't really matter so much. So yeah, Atom is still very popular, but more and more often people just use rmsprop or rmsprop with momentum. Another variation of Adam is called AdamX. And this is actually a simplification. Instead of um, computing this correction factor that was used by rmsprop and Adam, it replaces this by simply the maximum of the current gradient and the previous maximum scaled down by a factor gamma, so like 0.9. So this effectively measures what was the recently observed highest gradient. Right? And that's roughly what you want. You want to correct the learning rates by the relative scale of the gradients that each individual weight has to deal with. And this also achieves this. Whether it's better or not, it depends. I've seen cases where AdamX does a lot better than Adam or rmsprop, but let's compare. So if we compare Adam to AdamX, it's probably very similar. But like I said, there could be cases where it actually makes a difference. If you compare Adam to rmsprop, we'll see one big difference, and that's exactly this bias correction. But remember when we said that rmsprop has a problem that the initial steps are quite small, and Adam corrects this by this bias correction, and this effectively makes the first steps quite big, which, well, in this case actually causes some overshooting, but it's not too bad, right? It still works very well in general. Actually, another fun anecdote is that Adam is not proven to converge. There was a proof, it was proven wrong. So Adam is not supposed to converge, but it typically does anyway. So that's an interesting and not uncommon case where the theory deviates from the practice. We can also compare Adam with rmsprop with momentum, and then, well, this also gives rms more punch in the beginning. And yeah, it actually gets there a little bit faster than Adam. It actually gets close to the optimum as well, in fewer steps than Adam. So this is another scenario where rmsprop with momentum works better than Adam. But again, your mileage may vary, and it's good sense to try them if you have the time. Try different of these optimizers on your dataset. If in doubt, I would start with rmsprop, maybe rmsprop with momentum, and see if that gets you there. If not, try some other ones as well. And this brings us to the end of our entire SGD zoo. So you've seen a lot of these different techniques. And you'll see that they all have different characteristics, right? So some of them start very small, like normal SGD variants, except for SGD with decay, which has a very large initial learning rate, but then decays fast. We see that the momentum variants, they all overshoot in the beginning, some more than others. And we see that rmsprop here, it's still in the beginning. It's already curving to the correct direction, but it's not quite there yet. So at this point, SGD decay is sort of winning. If we leave it for more iterations, we will see that gradually, especially rmsprop with momentum is going directly to the target, followed by SGD decay. Then momentum is also gaining. As you can see all of these. So at this point, rmsprop with momentum is starting to bounce around a bit, while Nesterov momentum actually goes pretty directly towards the optimum. So yeah, rmsprop with momentum got there fastest, but then starts jumping around because the momentum is still too large, and it will take a while before it actually finds its optimum. While the purple one, Nesterov, is I think pretty close now, as well as momentum. So they are both. This is another scenario where rmsprop works well, but just SGD with a good schedule also gives you a good result. In the end, they will all get there, of course. Just some are faster than others, and this is still a quite smooth scenario. The surface is still quite smooth. In real life, it can be that some of these converge and other ones don't. In general, rmsprop is shown to, well, in practice, not theory, but in practice at least, it's shown to converge pretty well in most situations. It's pretty robust.